this question might be more specific to the one person who asked it, but I figured it was worth mentioning as well, hopefully briefly. Dhrystone in this particular case is just a benchmark, a synthetic measure of processor performance. Essentially, it does a bunch of so-called common operations and effectively measures how long those operations take. And the reason why this is useful or interesting is that if you compare processors simply by how many instructions do they perform per second, you're going to get a misleading comparison, because you could have a processor that has more complex instructions that take longer take multiple cycles per instruction, but might do more as well. So just saying, oh, I completed 10 instructions and I can do well, 10 million, whatever the number happens to be, instructions per second, isn't necessarily a useful thing in and of itself, unless you're comparing two processors that are identical in every other way, like two processors that are supporting the same instruction set and are implementing that instruction set in the same way. Then maybe you could compare them in terms of MIPS. But some sort of benchmark to compare processor performance is kind of the more practical way of doing it. And this particular question asked for Dhrystone MIPS or DMIPS, and I actually had to look this one up because I hadn't heard of Dhrystone MIPS. But it's just your Dhrystone score divided by 1757, which happens to be the score maintained on an old VAX machine that it was ostensibly a 1 MIPS machine. So I think the question of like, what is Dhrystone is probably, well, I would be surprised if that was asked on a regular basis in an interview. But I think what it's getting at, which is comparing processors and potentially comparing different architectures and instruction sets, understanding how they're working in some ways from an assembly perspective, and in some ways, like how is the architecture actually processing instructions? Because there's ways, for example, with pipelining, that instructions might take more time individually, but the entire program might take less time overall, kind of a thing. So understanding that concept is probably worth a little bit of digging, a little bit of understanding. And I wanted to answer that here now because of that. Let's see here. It is 7 o'clock my time. It's been an hour, probably a good time to take a 5-minute break for folks to get a snack or water or something. And let's come back together at 7:10 to continue making our way through this. And like before, feel free to post any Q&A questions in the chat or in the Q&A box as we are gone, and then we can talk about them when we come back together. All right, here we are, 7:10. Let's come on back and get this ball rolling again. One of the topics we talked about on Sunday was, generally speaking, callback functions and how you might register for them, whether it be a one-off registration such as a asynchronous write to a USB pipe, for example. We also talked about periodic registrations. I think I used the example of sensor events. Obviously, another common periodic event would be a timer, registering for a periodic timer callback. So those are all different types of registrations. And I was hoping to talk about, and someone actually posted a question about this too, so I think it works out nicely, is what does it look like from the other end of the things? What does it look like to implement a callback function, or implement some sort of mechanism like this? And this ends up being a not uncommon question for MAP. The MAP operation effectively exists innately for some languages, like Python, for example, but doesn't exist as a general purpose language utility in C. But conceptually, what I'm calling MAP is we want to apply some caller provided function for each entry in an array. So the caller is going to give you an array and give you a function, and you're expected to invoke that function to modify that data for each entry in the array. That's the problem statement. And logically, this is a simple problem, but the solution for this kind of involves being familiar with function pointers and arrays and casting and pointer arithmetic and all those other sorts of things. So let's look at it first from the perspective of the caller, from someone using this. So let's pretend that there exists a function called map, and oops, there we go. Let's assume that there exists a function called map, although we're going to look at this actual prototype here in a second, but I wanted to set the stage first. So we have an input array of size 10, which I happen to be an array of integers, and then we've allocated buffer space for an output as well. We're going to call this map function here, providing our input, our output. This 10 refers to how many inputs and outputs are there. I'm going to provide my function pointer, which is what I wrote up here. And then what I'm also going to provide here is the size of each entry in my array. We talked how void pointers were a powerful thing. If I had a map function that took in an int array and had an int out and so on, that would be great, fine and dandy, but it would at least strongly imply, if not require, that the input and the output were always integers. But the problem statement here said that I needed to provide some function for each entry in any type of array. So I need to make use of void pointers as part of my function prototype. So rather than accepting ints, my map function is going to accept void input and output arrays. And C is more than happy to cast this back and forth because input is simply a pointer and this in down here is simply a pointer. So going from one to the other is fine and dandy. But then conceptually, the challenge, when we actually want to implement map, if someone gives you an array, how do you know how big each entry in the array is? Because let's think about what an array is. In memory, if this is, for example, a uint32 array, we're going to have 4 bytes in each one of these fields, so on down the line, such that the entire thing, in this particular case, is going to be 4 times 10. So it should be 40 bytes. But if I instead had used uint16, then each entry in my array would instead be 2 bytes. And my total size would be 2 times 10, 20 bytes. So I'm passing in a pointer. I'm passing in a pointer to the beginning of my array. And we know, because we're passing in 10, we know that the array has length total 10. But once again, this array size of 40 bytes requires knowing how many entries are there and how large is each entry. So anyways, we're going to get to the implementation in just a second, but I wanted to point out the importance when you're using things like void star is you typically either need to have innate knowledge or need to provide some other manner to provide that context, that information about what the void star is actually pointing to. In this particular case, my callback function, my manipulation function, all we're doing is taking the input and adding 1 to it and spitting it in the output. But because, once again, this is a general purpose sort of tool, the inputs and outputs are both void. And I can't say input plus 1 if input doesn't have a type. Void being kind of the typeless type, if you will. So in order to actually do something useful, I need to cast it to some temporary variables in and out. Once again, I'm the one that called this map function. I know that I'm passing in uint32s, so I can safely cast them back to uint32s over here. But from a library perspective, from a general purpose map implementation perspective, everything needs to be void stars because it needs to be able to support any potential type. Okay, let's look at the actual implementation, then maybe we can jump back and forth to some of these things. Might be able to answer some more questions before they happen that way. Here's my implementation of map. First is worth pointing out that we have our void star input and void out array, our array length. I'm putting the mandate that the input and output arrays have to be the same length. Conceptually, it made sense to me. We have to have our callback function. And then we have to know how long or what is the size of each element in our array. This is just the prototype for the function that we were just using a second ago. So hopefully this answers some questions. And this right here is our callback function or our application function. And I define that using a type def right up here. And this is the syntax, I think we showed it on Sunday as well, for having a function pointer. And I would say it'd be worthwhile to understand how function pointers, in at least kind of basic forms like this, or function types as well, can be written in C code. So in this case, once again, we have the general purpose void as their input and output array, and then the general input and output for our callback function. The actual implementation ends up being conceptually simple, but a little bit dense in terms of code. And I mentioned this the other day as well, but void stars aren't particularly useful when you have to actually do memory manipulations with them. And C provides a standard type, both a signed and unsigned version of it, a standard type. And all this is an integer whose size is greater than or equal to the size of a void star. So uint pointer is always guaranteed to be a large enough integer to fit a pointer into. So hence it ends up being a safe thing to use when you were trying to do pointer arithmetic. We obviously could have actually defined this interface. So rather than using void up here, we could have used uint pointer as our parameter data types. And I've seen some interfaces do it that way, although more likely than not, I usually see it as void star. And I think that's because it's logically a more coherent thing to do. Like if you want someone to pass you a pointer, you give them a function parameter that involves a pointer. And when you start using int pointer, it can be a bit ambiguous, like what is it exactly you wanted me to do? So regardless, the interface had a void star. We need to convert those into an integer type so that we can actually do some interesting arithmetic with them. And then we need to, as you might guess, loop over every entry in our array and then call the callback function for each one. Looping over the array is pretty straightforward. We know the array length. We start from 0. We go from 0 to array length. But what gets a little bit complicated is we need to know in our big glob of memory where are these dividing lines? Are these 4, 4, 4, 4, 4, 4 in terms of our array? Or is this 2, 2, 2, 2, 2, 2, and so on? So in this particular case, we need to first pass in the appropriate input, and the appropriate output pointers, so that the input data is aligned for what it logically is, and the output data is aligned for what it logically is. And this is where that pointer arithmetic comes into play. We have our input pointer, which starts off, it continues to be the pointer address at the beginning of the array. And then we're going to add some sort of offset to it. Offset's going to start off with 0. And we do the same thing with the output. Because once again, our two arrays are going to be the same size and are going to progress in series. So we can essentially do the same thing for both of them. So the first time this runs, offset's going to be 0, and we're essentially passing in the first entry of the input array and the first entry of the output array. But then the second time around, we need to make sure we pass in the second entry. And the second entry is element length, or in the case of our example, 4 bytes into our array. So our element length here is 4. We can add that to our offset. So offset now went from 0 to 4, and now we're adding in 4 to get that second entry in our array. And the next time we do it, it's going to be 8, and so on down the line. So each time we're invoking our callback function, we're essentially incrementing the address of the array entries by 4. And the beauty of this is that if, for example, you wanted to have an array of shorts or an array of 64-bit integers, you could pass whatever length you wanted here. It's also worth pointing out that this isn't limited to basic data types. There is nothing in this implementation, and frankly, nothing in the original prompt that limits it to a basic singular data type. This could be an array of some sort of structure, and each element, each structure size could be 1K bytes, any sort of arbitrary length. This general purpose is going to work for all of them because we did things like using void pointers. And this is obviously just one somewhat contrived example for something like map, but we talked about some examples on Sunday as well, where let's say you have a registering for sensor data, but you don't necessarily know what kind of data you're getting. The infrastructure doesn't know what kind of data you're getting. You know what kind of data you're getting, so you can cast it appropriately. The infrastructure just needs to know how big something is so that we can offset accordingly. Any questions at this point regarding this, both the map implementation, but also kind of more conceptually what it is we're trying to do here?
Glenn, can you just say again why do we need uint pointer type instead of void?
Oh, excellent question. So, as folks are probably aware, if you have, let's create a new page here. If you have something like this, a pointer to a uint32. And if you say I plus 4, let's dereference it. What this conceptually is doing is, let me actually explain this a little bit differently. This will be easier. Let's say we have an int array of size 10. Doing this nomenclature here is saying dereference 4th entry in the array. and I'm assuming folks have probably seen this sort of syntax before, such that array, these two lines are essentially doing the same thing. Oops. Yeah, I'll stick it at that for the moment. So what the sorry, I doesn't mean anything right there, so I renamed it R+4. That might
Yeah,
help
but
smooth
yeah,
that out.
it was from the context. It was
Okay, cool. So that's how the C language works. If you have a pointer type, and this right here is effectively a pointer type. You could just, this is almost the same thing as thinking of it as a pointer R. If you have a pointer type and you add to that pointer type, under the hood, it's doing effectively a size of type times X. So in this particular case, it's doing a size of uint32 times 4. And it's treating that as the address that you're going, or the data that you're going to ultimately try and dereference. So that's what's being done automatically on your behalf, which in this particular case is great, because if you want to access the 4th entry in the array, then this makes it nice and easy. You don't have to do the math yourself. The challenge here is that, well, it's twofold. If you have something like, if we had instead used uint32 pointer, not that we actually intended it to be a uint32, but if we had just said, you know what, screw it, we're going to use uint32 pointers because I really like uint32 pointers, then down here, if this was your out array plus offset, what that is going to end up doing to you is a size of uint32 times offset. And what we wanted to do here is treat offset as a number of bytes. So we're doing the starting address plus some number of bytes. But when you start having this sort of thing going on, what you've essentially done is said out plus offset times 4.
so is it really because we cannot do pointer arithmetics on void pointers, right?
Yes, I was trying to get the more detailed answer, but yes, you're absolutely right that this right here still works. I mean, it's legal code. It just isn't going to do what you want, because we're doing the size of and then multiplying that by the offset. And yes, size. Sometimes I get on a little bit of a tangent, but you pointed out exactly right that if we had here our void stars, we would essentially be having something like size of void times offset. And void doesn't have a size.
Okay. So do you think it would be a compiler error, or would actually give us size of void 0 and then we would get the wrong answer? I'm just
That is a good
guessing.
question. I'm pretty sure it's defined to be a compiler error. Like I think the C spec says it's a compiler error, but I've honestly never done it before. So I suppose I can't say with complete confidence. So the reason why I'm casting the uint pointer is so that I can add the exact number of bytes I want to the start of my array. The start of my array being either in array or out array. And I want to add a specific number of bytes where I'm keeping track of that in this local variable offset. I mentioned how if we used some other arbitrary pointer type, we might end up getting an incorrect offset applied. We just mentioned how if we use void, it probably wouldn't compile at all. There is one other approach that I see done commonly. So you'll probably run into this as well. I think uint pointer is the clearest, most concise, and most likely to be written correctly approach to this problem, but it is not at all uncommon to instead see someone doing something like uint8 underscore t star in equals. So this line right here doing this instead. A lot of people will cast all of their opaque data types to a uint8. And in fact, some people might even have written this as uint8 pointer up here. And it was kind of thinking like uint8 as a byte array. So I'm going to cast everything to a byte array and then do all my operations. And the upside to that is if in and out were uint8 pointers, this math actually works out correctly again. So it's a very common way to see uint8 pointer, uint8 star as your kind of opaque data type, either instead of void star and or instead of int pointer. There's probably nothing wrong with it. I bet you there's other people out there who say that that is the correct way of doing it for X, Y, or Z reason. This just happens to be the way that I think makes more sense and works better with kind of the C language specification. But both approaches are totally valid. What isn't valid, once again, is doing something like int32 as your opaque type, because then it's both going to look confusing and not give you the right pointer arithmetic. Sorry, go ahead. There was another question.
Yeah. So if the function we are using uint32 pointer and we cast in the function to uint pointer underscore t, it's still going to do arithmetic according to uint32.
Yes, but once you switch to int pointer or uint pointer, you're now doing integer addition. So like this right here, this out is literally an integer, and we are adding one integer to another integer. There's no pointer arithmetic, technically speaking. We are adding one number to another number, and then we happen to be casting that to a void star. So uint pointer is an integer just like any other integer in that sense. It exists only to be a convenient integer that's always guaranteed to be big enough.
So we don't need a void pointer in that sense, right? Even if you use one uint32 pointer, you're still going to work. But for general function, we can use a void pointer.
Right? I'm not quite sure I understand. Can you say that again?
So if we use a uint32 pointer and we cast it to uint pointer, so you're going to get arithmetic as 1 byte each, right?
Yeah, but casting something to and from a uint pointer doesn't change the value. So a pointer is just an address, is just a number. So casting something to an int pointer doesn't change that number, doesn't change the value. In fact, if you were to look at this line in assembly, well, it wouldn't be there in assembly because this cast does nothing. All we're doing is giving a hint, not a hint, we're giving directions to the compiler for how to interpret this value, but the value itself is staying the same here.
Yeah, thanks. Thanks, Glenn.
Glenn, first time I'm seeing the uint ptr underscore t. Is it same thing as like uint34?
Exactly. They're all defined in standard int.h. They're also part of the C spec, so it's not like you're doing anything crazy, but they're all there for you in the same header file. What is worth mentioning, and I think I've said this before, that in many contexts, you want to use a fixed length data type. That there's some really good benefits to knowing how large your data type is. And we're going to go into even more of those examples this upcoming Sunday when we're talking about structures and trying to figure out how fields within structures are aligned. This uint pointer kind of ends up being an exception to that, because an int pointer, uint pointer is, the size of it is going to be big enough to hold a pointer or an address on that particular architecture. So a uint pointer sometimes is going to be 64 bits and sometimes is going to be 32 bits. So it's not actually a fixed length type like the other ones are within that file.
Okay.
So I wouldn't use uint pointer as part of like the contents of a message, because it might not be the same from architecture to architecture, but it ends up being a very useful tool if you wanted to write code that would work well on a 32-bit machine or a 64-bit machine. This is kind of the solution to that problem.
If it's a 64-bit machine, then your in array and out array, whatever you pass, right? Those are 32-bit uint 32. But here, uint PTR, since it's a maximum size of address is going to be 64-bit, right? And 64-bit when you declare as uint point PTRT.
Oh, so it's worth emphasizing here. So on this previous page, we have these uint 32's inputs, which once again, that's just a pointer. So we're passing in a pointer here and a pointer here. And then on the next page, we're taking in a pointer and taking in a pointer. Pointers are always going to be either 4 bytes or 8 bytes or whatever the appropriate number of bytes for that particular system. They're always going to be the same length for every data type, regardless of what it's pointing to. So a uint 32 pointer is the same size as a uint 8 pointer, is the same size as a void star, is the same size as an int pointer.
So that means on 64-bit architecture, the address bus may be 64-bit, address bus is 64-bit, and then both uint PTR and then the uint 32, whatever you declare, points to the 64-bit address?
Yes, that's correct. Uint point, these right here are all going to point to 64-bit addresses in that particular case.
Yeah, uint 8 and uint 32 and uint 64 and uint PTR, all of them points to 64-bit address on a 64-bit architecture.
On a 64-bit architecture, as a general statement, all pointers are going to have, if you do, for example, a size of whatever that pointer data type is, it's going to return 4 or 8 to you.
So it's not a generic statement then. So it's 4 or 8 depends on the architecture you're saying. If it's 32
Oh yeah, totally, yes. And if you were on a 16-bit machine, it might return 2. It's going to be however is big enough to support the addressable memory space on your system.
Okay, it's going to be 2, 4, 8. Okay, got it.
Yeah.
Thank you.
Glenn, I have one concern because this type is uint pointer underscore t. Does it mean it's the same as uint 32 underscore t star? Sorry, is it the same type as unsigned int star?
Okay, let's see here. So you're asking the same type or the same size?
I'm talking, is it the same type? So for example, okay, so let's write it down. So uint pointer underscore t, is it the same type as unsigned int star?
Is it the same type? No.
Is it because it has uint in name, so kind of implies it's unsigned int, is it not?
This is an integer type. This is a pointer type. So inherently, those are 2 different types from the C perspective.
Right,
what you could ask potentially is unsigned int. Is unsigned int the same type as uint pointer? Maybe that's another question you might want to ask.
For example,
and then the answer there is yes, on a 32-bit machine. On a 32-bit machine, these are likely typed def to be the same thing. Obviously, on a 64-bit machine, this would need to be type def to be something bigger so that it's 64 bits. Did that answer your question?
Yeah, so I'm just thinking aloud. So when we add an offset to uint pointer underscore t, this is not really pointer arithmetic. It's a normal arithmetic operation between one integer type and another integer type.
That's exactly right. So I said there's a lot of writing on here now, so hopefully you can try yellow. This line right here is just simple numerical arithmetic. We've taken in happens to represent the pointer, but conceptually it's just a number. And from the perspective of the compiler and from the perspective of C, this in right here is just a number. And we've added another number. This offset happens to logically represent a number of bytes that have been offset or should be offset, but it's also from a C perspective, it's just another number. And that's why we have to cast it back to void to turn it back from an integer type to a pointer type.
Yes, okay.
And I think we talked on last Sunday about implicit and explicit conversions. And here you actually have several examples of that. On this page, we are doing an implicit conversion from a uint32 pointer to a void star. And that's or at least should be a legal implicit conversion. Like we're not explicitly telling the compiler to convert it, but it's doing that on our behalf. But in this case, we have to explicitly tell the compiler, I'm just going to keep highlighting it up here. We have to explicitly tell the compiler to cast from a pointer to an integer type. Those are inherently, from the C's perspective, incompatible types, and incompatible types have to be explicitly casted. But we know that they're compatible, but from the compiler's perspective, int and pointer are two different types that you cannot implicitly convert between. Oh, and I see, sorry, I see Bhushan has, you shared the type. Is this the type that you copied somewhere, or is this part of your question?
No, it's just from the STD int. Just wanted to share.
Cool. Thank you for pointing that up. Yes. So on presumably you're looking at it from a 32-bit machine, then those would be type def to the same thing. And I presume in the same file, if you look at what the definition of an int32 is, it's probably typed def to just a basic int type, I presume.
Yeah, it's an unsigned int.
Unsigned. Oh yeah, unsigned in the case of unsigned. Yes. Yeah, it was one of the nice things about the standard int types is you can look them up potentially for yourself on your particular architecture by looking into the library header files. The same thing goes, we'll talk about Indianness next on Sunday as well. And for little Indian versus big Indian and converting to and from them, there are standard libraries that already exist that will do some of this stuff for you. And you can take advantage of the fact that the compiler knows what kind of system you're on to do the right thing.